Have you ever looked up at the sky and just wondered, how does a 500-ton hunk of metal even get off the ground? Well, the answer is this incredible piece of physics called Bernoulli's equation. And today, we're going to unpack how this one elegant idea explains so much about the invisible forces all around us. I mean, it really does seem impossible, doesn't it? How can thin air lift something so massive? The secret, it turns out, is all about understanding how air behaves when it's moving. So let's start at the beginning and meet the genius who first cracked this puzzle. All right, first up, the equation of flow. Before we get to the principle itself, we got to meet the man who gave it his name and really laid the foundation for modern aerodynamics. And that man was a Swiss physicist named Daniel Bernoulli. Way back in 1738, he published this revolutionary work that, for the very first time, spelled out the relationship between a fluid's speed, its pressure, and its height. This one concept, seriously, changed everything, from how we design ships to, you guessed it, how we fly. Okay, section 2. Let's deconstruct the formula. Now, we're going to look at the equation itself. And I know, equations can look a little intimidating, but I promise you, the idea behind it is actually super intuitive once you see the pieces. So here it is. What this is really saying is that for any fluid moving along a nice smooth path, what scientists call a streamline, its total energy stays the same. It's always constant. That total energy is just the sum of three things: the static pressure, the energy from its speed, and the energy from its height. The big takeaway here, that total number on the right, it doesn't change. You know, the best way to wrap your head around this is to think of it like an energy budget. The fluid has a fixed amount of energy to spend, and it can spend it in three different ways. If it decides to spend more on one thing, like speed, it has to spend less on another, like pressure, to keep the budget balanced. The total energy is always conserved. So let's look at that budget. First, you've got pi, the static pressure. This is like the random internal pushing of the molecules in every direction. Then you have the dynamic pressure, which is all about the energy of motion, the kinetic energy of the flow. And finally, there's hydrostatic pressure. That's just the potential energy the fluid has because of gravity and how high up it is. All right, so we've met the equation. Now for section 3, the big principle. This is it. This is the single most important idea to take away from all this, and it's what we call Bernoulli's principle. To really see this in action, just picture water flowing through a pipe. It starts out wide, then it gets narrow in the middle, and then it opens up again. So what happens when that water hits the skinny part? Well, for the same amount of water to get through that smaller space, it has to speed up, right? Its velocity has to increase. That part makes total sense. But here is the million-dollar question. What do you think happens to the pressure when all that water starts moving faster? And this is the heart of Bernoulli's principle. As the speed of the fluid goes up, its pressure goes down. Let me say that one more time, because it's everything. Faster-moving fluid exerts lower pressure. I know, right? That feels completely backward. Our brains want to think that faster means more force, more pressure. But you have to go back to that energy budget. To get that extra energy of motion, that kinetic energy, the fluid has to pay for it from somewhere. And it pays for that new speed by giving up some of its static pressure. Moving on to section 4, real-world applications. Okay, once you really get that one simple, counterintuitive idea, fast speed, low pressure, you suddenly start seeing it absolutely everywhere. Let's run through a couple of examples. And we're back to our airplane. A plane's wing is curved on top. That special shape forces the air flowing over the top to travel faster than the air moving underneath it. And what did we just learn? Faster air means lower pressure. So you get this zone of low pressure above the wing and higher pressure below it. That difference creates a net upward force, and that, my friends, is lift. It's also how a Bunsen burner works in a science lab. You've got a jet of gas shooting into the barrel at super high speed. This creates a low-pressure zone that literally sucks oxygen in from the outside air, which then mixes with the gas for a nice, clean burn. Engineers use this concept all the time in something called a Venturi meter. It's really just a piece of pipe that gets narrow and then wide again. Because of Bernoulli's principle, we know the faster the fluid is going through that narrow part, the lower its pressure will be. So by just measuring that drop in pressure, you can figure out exactly how fast the fluid is flowing. It's so simple, so reliable, and there are no moving parts to break. Just brilliant. And that brings us to our final section, knowing the limits. Look, Bernoulli's equation is incredibly powerful, but it's not some kind of magic formula that works for everything. It's a simplified model, and to use it right, you have to know the rules of the game.
So, for the math to really hold up, we have to make a few assumptions. First, the flow has to be steady and smooth, not all chaotic and turbulent. Second, the fluid is assumed to be inviscid. That's just a fancy word meaning it's not sticky. So we're basically ignoring friction. And finally, the fluid has to be incompressible, meaning its density stays the same. That's a pretty safe bet for water, but it gets a little trickier for gases at really high speeds.
So there you have it. From a massive jetliner to a simple lab tool, Bernoulli's principle is this fundamental concept that quietly shapes our world. Just remember that simple, inverse relationship, where velocity is high, pressure is low. Now that you know the secret, the fun part begins. Start looking around you. Where else do you see this elegant idea at work?